Working with probability, we want to start with some basic understandings, and in that we're going to talk about the set theory and Venn diagrams, something that has probably been covered with you in math and different subjects before now, but we're going to talk about it and use it with probability. And in this, we're talking about what are sets and how can they be represented, and we want to learn how to interpret sets and set notation. We're going to identify some of the key vocabulary, elements, universal set, empty set, subsets, those kind of things. And then we're going to use these Venn diagrams and set notation to represent the unions and intersections in those empty sets. So that's where we're going to begin. And in doing so, let's look at our set builder notation and a set. A set is an infinite or finite collection of items. And finite means that the set has a specific number of items, and then the infinite means that it is not possible to list all members of a set. And then, of course, set builder notation allows for the symbolic representation of a set. So if we look here, we have set S, and it's for all values of x such that the condition for x applies. So let's see here. Consider the set of integers. So we have this set of integers, or could also be represented as 0 and then plus or minus 1, 2, 3, 4 on to infinity. And these sets would be an infinite set, right? Because it goes on forever. That's sort of what our ellipse is indicating. They're infinite sets. And in set notation, it would be n is equal to x such that x is an integer. That's one way we could write that instead of having just another way we could write it. And then if we look here, we have g is going to be x such that all values of x are greater than 6. So basically a set of numbers greater than 6. And looking at the components of sets, let's see here, we have, a set is a collection of items such as the objects, peoples, or numbers. So we have this set. Let's see here, an element is an item in the set, right? An element. All right, so the Greek letter epsilon right here identifies an element of a given set. And then the epsilon with a slash through it identifies an item that is not. It is not an element of a given set. So looking here, we have set S, 0, 1, 2, 3, on to infinity. Or in set notation, we might be looking at x is all values of x as a non-negative integer. Let's see, let me write that in here. So we have s such that x is all value is a non-negative integer, because 0, of course, is neither positive nor negative. And is 10 going to be a member of that set? Well, 10 is a non-negative integer, so it is going to be part of that set. Negative 5 would not be part of that set because it's a negative number. Looking at the other example here, we have given that T is going to be Abby, Brian, Carl, Darren, and Evan. We're trying to figure out, is Brian, Frank, and 10 part of that set? Well, let's see here. Brian is part of that set. He's an element. Frank is not a part of that element. And then 10 is also not an element of set T. So just trying to distinguish between something being a member of a certain set or not. Let's see here. So as we move on, notation for specific sets, the U, that represents the universal set, or the set that contains all the elements under consideration. So let's see here, all. This is considered, it represents an empty set, the set that contains none, no elements let's see here, and then We have A is a subset of B, so this reads A is a subset of B, which means that A is again, a subset of B, or that every element of A is also an element of B. B may be larger, there may be more selections in the B set, but A is part of it. And we're going to do some examples here in a minute. And then this is indicating a complement, X such that X is not an element of A. So it's going to be everything else. Okay, so it represents a complement of set A and the set elements in the universal set that are not in set A. And the complement. The complement of set A in all elements in universal except those in A. So we're talking about an empty set here. An empty set is a subset of all other sets, and the empty set is a complement of the universal set. So if the universal set, it is composed of everything, then the empty set would be its complement because it would be all others. And again, we're going to talk and see practice some activities and exercises here. So looking, we have example 1 here. It says, let's see here, let U be a set U such that X is a Roane County High School student. Okay. Set A is going to be all of Roane County High School's juniors or seniors. Set B is going to be all of our freshmen or sophomores. Set C is going to be the seniors who play football. And let's see here. So set C is going to be a subset of A. So C again is going to be a subset of A. C is the seniors who play football. Now, A is all of the juniors and seniors. So that's why C is incorporated inside of A. We have all of our juniors and seniors here. And then right here, we got set C, which is going to be our football players. They're inside of, all of them are inside set A. And then we have AC, so our complement to A is going to be B. So we talk about all of our universal set is all of our students. Well, if A is including, if A is including all juniors and seniors, well, then the other portion of that universal set would be my freshman and sophomore. So that's why this would be, B would be its complement. So between A and B, they've included all of the universal set. And that's where they're going with that. So if we look at example 2 here, they've given us a universal set list of numbers. And as we can see, we have 1, 3, 5, 6, 7, 10, 12, and 15. These are all part of our universal set. Then we have A. A is going to be just 1, 3, and 5. Well, if I look over here, these numbers right here are set A. Okay, so that includes set A. So the complement of set A is going to be all other numbers in the universal. So the complement is going to be 6, 7, 10, 12, and 15. So there we go. 6, 7, 10, 12, and 15. So between A and its complement, that should encompass all of our universal set. Now, when we start defining a union of sets, let's see here, using our Venn diagram. A Venn diagram is going to be a graphic organizer representing the relationships. So the Venn diagram is a graphic organizer representing the relationships among groups or sets. The union of two sets is all elements in either set or both sets. And then so here we have representing the union of A and B is going to be X such that X are elements of A or X are elements of B. So here we have this universal set. We have a combination of set A and set B. and then some places where we have A and B overlap or intersect. So the rectangle represents our universal set, and then the intersection of the two or more sets is all elements that are common, right? Because these are going to be things that are going to occur in both sets. And sets notation is not, if you saw before, we were talking about the universal set is either or. Here, it's going to be the A intersects B such that X is all values such that X is an element of A and an element of B, because they're going to overlap, right? They're in both, so that's that intersection point. And then if we look at example number 3, we have the union, and they've given us some information, and we're going to go ahead and fill it in over here on our Venn diagram. But the universal set is going to be -14, -11, -9, -3, -1, 2, 5, 7, 12, 15, and 14. And they've said, hey, A is going to be X such that X are all elements of the universal set and X is an even integer. B are going to be elements of our universal set and X is divisible by 3. Then we are going to have the union is going to be right here, and the little typo right here, huh? And then the intersection points are going to be 12 and 24. So as we fill these in, I guess really let's just start filling in some numbers, and gosh, that should be 11 right there. But we know they're going to intersect, and this is going to be our intersection point, A, and we're intersecting, so we have 12 and 24 are going to be within that intersection because that's what they're saying is part of both elements. So I can go ahead and eliminate that from my universal set. And looking here, I'm looking for even integers to be part of A. So even integers, I have -14, that'll be an A. 11, 9, let's see, 2 should be an A. And I think that's all for my even. So I should have -14 and I should have 2 over here in the A set. So get that, cross that out. And the set B are going to be divisible by 3. So looking here, I have 15 is divisible by 3. I can use that. -3 is divisible by 3. And I believe that's it. So the remainder of my numbers are part of my universal set, but they are not in subset A or subset B. So we end up having to just get them in here where they fit. So -9, -11, -1, -5, -7. I'm sorry. That is a +5 and +7. So I think I have now all my numbers accounted for. So that's what my Venn diagram would look like. Populating, and I populated from the most restrictive, and then I moved outward. So let's see here. So looking here, in example number 4, just giving 2 sets, I am trying to find out where set A intersects B, and that's going to be the overlapping. So I have a 2. I have a 2 in B and a 2 in A. I don't have a 5 or a 4 in both. I don't have a 6. Oh, it looks like both sets have a 10, and both sets have a 17. So that's going to be my intersection. My intersection is going to be 2, 10, and 17. So there you go. Working with my Venn diagrams, working with my sets to find some of that common information. Going on to intersections and subsets. So using this as an example, really, we just got a large example here. It reads, let U be all X values such that X is a student at the Barclay Academy. Okay, so we have a bunch of students right here represented in our Venn diagram. A is going to be all students, elements of the universal set, and X such that, these students are taking geometry. So set A over here is going to be my geometry students. Looks like I have 3, 6, 5, 8 different sets of students. Wait a minute. Set A. Yeah, 8 different sets of students here. And there, so we have, let me see here, I got an 8 plus 6 plus 5 plus 3, all totaled, I hate doing math in public. I think that's going to be 22 students taking geometry. And then continuing on, B, X such that the students are taking biology here. So it looks like we have 10 students plus 5 students plus 3 students all taking biology. So we have 18 students there. Then set C is going to be our students taking literature. So here we go. We've got 14 and 5. So 14 plus 5, I got 19 students taking literature. And let's see here, Group D is in the math club. So here we go, we got math club right there. And if you notice, Group D is completely encompassed by, it's a subset of Group A. So they're my math students, but they're also in math club. Let's see here. So there are blank students that are not included in any of these sets, and they're not taking any of the courses that are not, and they're not in math club. And that would be these students right here. We have 152 students out there in our set that are not taking one of those 3 courses. And it says now, this intersection right here, this is the intersection of set A, B, and C, which means that there are blank students taking all 3 courses, which tells me there's 5 students taking geometry, biology, and literature. And that's how we would distinguish and determine these, this information, by being able to interpret the data on our Venn diagram. Looking at the intersections and subsets. Now here, again, this is a long bit of information to talk about, but we have this ice cream company working on new flavors, has 50 people taste test the new creations. They're asked to pick the flavors that they've liked, and here are my results. So we have banana cream pie, we have pineapple upside down, and we have carrot cake. And looking at this, blank people liked only the carrot cake. Well, right there I had 7 people like only the carrot cake. There are blank people who liked only the banana cream pie. Well, 20 people favored the banana cream pie. Blank people liked banana cream pie and pineapple upside down. Well, these guys couldn't make up their minds, so I had 5 people that liked both. And then there are blank people who liked only the pineapple upside down cake. So 8 people out here said, nope, pineapple upside down for me. And then right here we have people didn't like any of these flavors. 10 people out here that chose not to select one of those flavors as their favorite or one that they enjoyed. So there you go. There is no intersections between sets B and C. So right here, those circles, those sections don't overlap, so there is no value in the intersection of B and C. Or should I say that it's an empty set? Now, continuing on here, example number 4, use the following sets to define each set below, okay? And then it says that my universal set is going to be whole numbers that are at most 8. Okay, whole numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8. There is my universal set. Now, let's see if I want to identify, I have A. Set A is going to be 2, 4, 5, and 7. Set B is going to be 1, 4, and 7. Now, as we look at this, now we can start to answer some questions. So, where do A and B intersect? Let's see, it looks like they intersect at 4 and 7. So that is going to be 4 and 7. The union of A and B is going to be all the numbers that are part of both of those. So that is going to be the union of, 1, 2, 4, 5, and 7. So that in the union, and then we have this notation here. It's asking us, what is the complement of A? Well, the complement is going to be all values of the union that were not part of A. So when we look at that, that is going to be 0, 3, actually, I skipped one, 0, 1, 3, 4 and 5 are part of it. We have 6, 7 is part of A, and then finally we have 8. So there's my complement of A. The complement of B are going to be all the values that weren't included in B. Well, B has 1, 4, 7, so we would have 1, 2, 3, 5, 6, and 8. So there you go. Those would be our complements to those. Remember, your set and its complement together should be all of the universal set. So again, your set and its complement, all of the universal set. A and its complement, all of the universal set. So moving on to a couple of more examples, we have here example number 5, given the two sets. Wait a minute. Yeah, given the two sets, determine if one is a subset of the other, and if yes, describe the relationship. Okay, all natural numbers less than 10. Okay, so all the natural numbers less than 10 are going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 2, 5, and 9, of course, are part of that. So yeah, B is going to be a subset of A. And let's see here, what else? A is all clubs in a deck of cards, and then all sixes in a deck of cards. Well, all sixes are not clubs, so that is not going to be, B is not a subset of A, so there's, nope, not. And let's see here, A, we have the months of a year, and then we have the months that begin with the letter J. Well, here also, B is going to be a subset of A because all the months that begin with J are also months of the year. So there you go, that's how we're looking at that. And then A, we have multiples of 10, and then we have multiples of 5. Well, think about multiples of 5, we got 5, 10, 15, 20, or you have multiples of 10, which is 10, 20, 30, and so on. Well, in this case, A is actually going to be the subset of B because all of the A values are going to end up also included in B, but not all of my B values are going to be in A because 15 and 5, those multiples of 5 there, those aren't going to fit in there. So that's how we would identify those. Let's see here, moving on to example number 6. The Venn diagram shows the number of senior boys who play football or wrestling. All right, so looking at our Venn diagram, looks like we have football players, we have wrestlers, and we have a bunch of students over here that don't do anything, that don't play one of those two. And then we have these that seem to be in the overlapping, so they must play football and wrestle. So here it's like, how many senior boys play football and wrestle? There's the combination right there. That's where they overlap. How many senior boys play football but do not wrestle? That's my football group out there that don't wrestle. So we have 18. And then how many senior boys play football or wrestle? Well, then we would have to add them all together, of course. So I have 12, 9, 18. I get 39 total. And then how many senior boys just wrestle? Or how many senior boys wrestle? Well, that's going to be a combination because they didn't omit football. They just said how many wrestle. So it's going to be total of 21. So there you go. That's how we're looking at that Venn diagram to answer our questions. Example number 7, we have a Venn diagram below that shows the number of people in a gym signed up for yoga or aerobics. So again, here's my yoga group. Here's my aerobics group. Here's the people that aren't signed up for either one of those. And how many people are signed up for yoga class? Well, I have both of these signed up for yoga class. So 64 plus 68 plus 24 is going to be 92. How many people are signed up for yoga or aerobics? Well, that would be 92 plus 89, and that should give me a total of 181. Then we have how many people are signed up for aerobics but not yoga? All right, so that looks like aerobics right here, but not yoga, 89. And then how many people belong to the gym? I'm going to go with 756 because I'm going to total, I've got 575. I have got 92 over here. I have got 89 over here for a total of 756. All right, let's talk about some travelers next by looking at this. Venn diagram shows the surveys of cities visited by a group of people on a recent trip to Europe. How many people visited Dublin or London? Okay, Dublin or London. So we have all of these people visited Dublin, and then all of these people visited Dublin. Well, all of these people visited Dublin. These people visited London and Paris. So we're looking for these added together. All of these people added together. And it turns out that we have, 89 plus 31 plus 64 plus 24 plus 43 plus 76 for a total of 327 total people visited Dublin or London. How many people visited London and Paris? So we're looking for that combo number, right? So London and Paris. Those guys visited London and Paris. These guys visited London and Paris. So for a total of 88 people. How many people visited London or Paris? Now we have an or, so we're going to add all of those up, and it's going to be a larger number. So looks like we have 95, 43, 24, 64, 31, and 81. We add all of those numbers up, we're going to get 346 total. Let's see here, 95, 43, 29, 24. 24, 64, 89, and 31 for a total of 364. Let's see, what's next? How many people visited Dublin and not London? All right, so here's my Dublin folks. These folks right here visited London. I don't want to include those, so these two totaled together will be the people who visited Dublin and not London for a total of 119. How many people only visited Dublin? We're looking out here. So these guys only visited Dublin. They did not visit London or Paris, so 76 people. How many people visited Dublin and Paris? Dublin and Paris. That would be these two right here are the intersections. So we're looking at 77, 67. How many people visited all three cities? Well, that's that magic overlap right there in the center. So 24 people visited all three. They were very active. And how many people visited London? Visiting London right here, it looks like we add up these four and we come up with 208 people. And then how many people took the survey? Well, Did they tell us in the beginning? They didn't, but if we add up all of these values, we are going to find out that 500 people took the survey. So there you have it. That's us using Venn diagrams and set notation and set data to help us organize information. So sets are collections of items that are either finite or infinite. Most of the examples that we've dealt with have been finite because we were able to count them. There was a set number. Sets can be represented symbolically using that set notation, including universal sets, empty sets, the unions and the intersections. And we also look at that visual aspect of being able to use a Venn diagram. So